שאלתי, מה ההסתברות להגיע מ-y1 ל-y3 ב-a ל-c? מה ההסתברות שאני ב-c בזה שהתחלתי ב-a? אז הדבר הזה הוא כמו מכפלה של שורה ועמודה. שורה ועמודה, נכון, לא כל המטריצה. וזה נותן לי את ההסתברות לעבור בעצם...
המטריצה היא נותנת לך? המטריצה היא נותנת? לכל מעבר אפשרי.
בדיוק, לכל מעבר אפשרי. ואני שאלתי על מעבר אחד, אז הוא פוזיציה מסוימת של מקום.
אז כאילו אני... אוקיי, המצב הראשון יהיה A, המצב השני יהיה...
כן, עכשיו המצב הראשון הוא פה והמצב השני.
זאת מטריצה חדשה, ואז אני אומרת, מ-y1 ל-y3, זה נפת לשורה 1 ל-3,
שורה...
או טור אחד
כן, טור אחד לשורה.
אז לקחת לו חשבתי שאני כאילו עולה ויש לי קצת יותר לנשום, נפלו עליי איזה 30 דברים שאני צריך לעשות, אז אני מתנצל שאנחנו לא כזה. דיברנו על חריג 6, כן.
אפילו לבדוק את חריג 5, יום לא יוכל לבדוק.
לא, לא הגשתי אותו. רק חיפשתי לי אותה ולא עשיתי לו שום דבר, כי חשוב. זה היה כאילו פורמי טראגי כזה, כמה הייתי נאיבי שחשבתי שהנה יש לי בדיוק מבחנים 3 ימים, איזה כיף.
לא יודע אם אתה עושה בזה שימוש שלו. מצאתי את זה. כן, זה טוב לשמור על זה.
כן.
זהו, כי אתה גדולה רגע יצא, אז לא מתחבר לי כל כך.
מה?
זה הגדולה ילדה?
ילדה. ילדה.
לא. שנייה רגע, נהיה קצת כזה, מה הולך? אתה ראית את הכתובת נעשה שישבתי איתך?
לא.
במעבדה?
לא, ראיתי את כרמל, אז היא אמרה לי שאתה למעלה.
היית במעבדה כבר?
הייתי עם מיקי.
אבל נכנסת לזה? נכנסת לחדר שלך? שבשת? והסתכלת על הלוח?
לא, הסתכל על הדוח.
שאלתי לך כמו כתובת נעשה. בשביל מה אני משקיע כל כך?
למה שאני אסתכל על הלוח הזה? אני הגעתי שם.
Markov chain. Now this is a special class of stochastic processes that generally have these two conditions. Y is limited to a discrete set of states time is discrete taking only integer values. So this is like what we had in our one-dimensional map that we saw. Okay. And stationarity, like we discussed just before the break, meaning that the transition probabilities depend on the time difference alone. Okay, it's stationary because if you look at this process at any point in time, you will get the same behavior. Okay, so it doesn't matter when you check it.
Can you write imagine?
Yeah, so this is, sorry. What does it say? Okay. So these requirements are not obligatory. Okay, so you might see that the Markov chain was defined for a continuous y, but a discrete time, or for a discrete y but continuous time. It's not very consistent in the literature, but the better, maybe the stricter definition would include all of these.
What did it say one? Y is limited to discrete what?
A discrete set of states. Set.
It's missing a word.
Set of states. Okay, now I said that y is limited to a discrete set of states, so it could be only integer values. Okay, but and then we have a further subdefinition of a finite Markov chain. So y is limited to a finite set. Okay, so these things make it a lot simpler for us. Now, P1 yt is just a vector Pn okay. So we can write a vector, it's finite, and it tells us what is the probability to be at each of the states that y can get at a certain point in time. Okay? And now P tau y2 given y1 is an n by n matrix. And I already showed this here during a simple case. So now we can look transition probability over multiple steps, okay, say tau is a period that includes 10 steps in time, and that would just be the transition matrix for a single step raised to the power of tau. Like we saw there, that we can just multiply the transition matrices. And then, writing a bit more simply, if we want to know the probability distribution, okay, this would be a vector, okay? So P of t would be P1 at time t, P2 at time t, and so on, till Pn at time t, P of t. This would just be that transition probability raised to the power of t that is now discrete, right? So this must be an integer value. This is an interval in time. And multiplying t0. This is the initial condition. And if you want to know where you are, or what probability distribution you get after a certain amount of time, you just multiply this by the transition matrix raised to a power.
This is the probability to be in the transition, is the initial condition?
Yeah, it's the probability distribution of initial condition. P0. This is for the initial condition, P0. So if you want to look at what happens from a certain initial condition, you could impose P0 equals 0, 1, 0, 0, 0. Okay? So you're saying there was a specific state to begin with. I impose this distribution, and then let's see what happens to it. Okay?
And you're saying what happens to it at t equals 5, for
Yeah.
example, right?
Mhm.
Not just at a general,
Yeah,
in general.
I'll show this as a simulation shortly. So the study of finite Markov chains is reduced to study of the transition matrices. Okay, n by n matrices, which have so we reduce this to the study of n by n matrices that have one non-negative element, of course, because they represent probabilities, and two columns that add up to unity within each column. Okay?
What up to unity is?
Unity is 1.
Up to unity.
Okay, so the probability to go from A to all the other states must add up to 1, including A. Okay. The probability to transition from A must in total be 1. And these matrices, just n by n matrices with non-negative elements and columns that add up to unity, are called stochastic matrices. Stochastic matrices. So you can just import anything you know from linear algebra about such matrices and apply this to studying finite Markov chains. Okay, so specifically, times P star equals P star, okay, then it means that you have an equilibrium state. And you apply the transition matrix to it, and you remain in that equilibrium state. So practically what you would do is you would investigate this matrix P. You would check, does it have an eigenvector? Okay, P star is an eigenvector.
It's not a vector?
It's a vector. P star is a vector,
Yeah.
and furthermore, it's an eigenvector of P.
Eigenvector.
Eigenvector with an eigenvalue of 1.
Okay.
Okay?
Now just,
So if you can find an eigenvector for T, okay, and its eigenvalue is 1, then that means that you have a steady state. Okay, your Markov chain reaches a steady state, and practically you would look at the eigenvalues and eigenvectors of T. Sometimes you'll get eigenvectors, for example, that that have negative elements. So this you must discard, of course. Okay, because we're talking about probability distribution. If you only got an eigenvector with negative elements, it means you have no steady state. If you got only complex eigenvalues, then again you have no steady state. I'll show this shortly. So this is P star is a steady state distribution. It's analogous to our fixed points in the dynamical systems, in the one-dimensional map, right? This is just what we did to define the fixed points. So this is a steady state distribution, and keep in mind that this doesn't mean that the system is now frozen and does not change. Okay, this might be a net equilibrium where the system might transition between states, but the distribution does not change. Okay, so you might have a system that includes 50 molecules or 500 molecules that undergo this process, this Markov chain process. Say our states are different excitations of the electrons to different orbits around the molecule, and the distribution dictates that you mainly have the lower orbitals populated. But it doesn't mean that all the molecules do not change. It means that molecules go from a low orbit to a high orbit and vice versa, but when you calculate the net change, there is no net change in the different states. Okay? You remain with 10% in this state and 20% and 30% and so on. But the molecules are all the time passing between the states, where on the whole there is no change in the distribution. Okay, so I'm going to give an example. I'm going to use a simulation for that. We just turned on the projector and the screen started showing down. Okay, one of the common examples for demonstrating Markov process is the random walk. Okay, say we have an ant that walks across a stick, and the stick is divided to different bins. Okay, so we can write a transition matrix. Okay, where say that at the first bin, it does not stay in one place. Okay, there's zero probability that it stays in this bin. there's a probability of 1/2 that it goes right, okay? And commonly, these things are, sometimes you need to decide how how to um, how to make it so that the column adds up to 1. So here we have circular 6. There's a probability of 1/2 to go to the last bin. Okay, like an old computer game. You go from that side of the screen and you turn from that. And if the ant is at the second bin, has an equal probability to go to each side, and so on and so on. Um, and so on. So this will be my my transition matrix. And we'll cut oxygen. Oh, okay. I don't know what's happening to the projector. Good. Okay. Okay, so I created my matrix T with what I talked about. And the n has the same probability to go to each side. And now I'm going to
But you
make,
don't have, in the first column, you don't have a half at the last row.
yeah, now I impose the circular condition. And now I'm going to impose that it starts at position 2. P21 equals 1. And then I'm going to run this calculation of what happens when you multiply it by the transition matrix, okay, multiple times. So these are the time steps, and here you see the probability as a heat map. So we started at number 2, and then as you see, we were forced to be either here or here, and then we had a high probability to be here and a low one to be here, but going out of the range and back. And as you can see, with time, our probability flattens, and we have a uniform probability to be anywhere, and this is a steady state. Okay, so you see here how the steady state emerges when you multiply the initial matrix enough times, the initial vector enough times by the transition matrix, finally you reach the steady state. And the steady state is something that you can also calculate analytically. Here I'm asking MATLAB to calculate the eigenvectors and eigenvalues of t. So you see that I found these eigenvalues, but this eigenvalue has this eigenvector, and it's invalid for probabilities, and also this one. This cannot describe a probability distribution. So the only one that can describe it is this. It's basically the uniform vectors. One, or I should basically normalize it. All of these should be 0.2 for a uniform distribution, and the eigenvalue is 1.
Is it possible to get more than one eigenvalue, one with two relevant vectors?
I think it is. I have one example that does it, and then your steady state might be a combination of these depending on your initial conditions. Okay, so before I move on to an example for something more complicated, I'll just say that you can reach the steady state distribution either analytically, like I did here, or you can just multiply many times and see what happens after 100 multiplications. Just raise t to the power of 100 and see what happens when you multiply.
It doesn't have to be uniform, right?
What?
It doesn't have to be uniform, the steady state.
No, it doesn't have to be uniform. Here, this was we have a random walk that is not biased and so on. Okay, so let's see when. Okay, I have. Let's write t equals 0, 1, 0, 0, 0. Okay, this was my initial distribution, and now I have my t, right? So I want to write t to the power of 100 times p, okay? And you see that I get this uniform distribution. So that would be the numerical way of reaching it. And you can also find analytically the eigenvectors. Okay, so next thing I'll do is, okay, let's look at this. So now I have this transition matrix where if the ant is at an edge of the stick, there is a probability that it will stay there. Okay. Another way to deal with the limit. Okay, so we see here that again. Oh, you know what? Yeah, we see here that again we reach this uniform distribution. Let's see. Yeah, and the initial condition does not really matter.
Why if you start at one, so
You still have a probability of 1/2 to move from there. Okay. There. So you see there is for sometimes there is a bias for that end of the stick, but it's cancelled out. And again, I can do the eigenvalues and eigenvectors, and again, this matrix also has similar. It has this eigenvector as well. These were a bit different, but they don't matter for us. I think there is before.
You take the eigenvalues of the original transition probability matrix.
Yes.
So
Because
there shouldn't be. It shouldn't. Of course, it shouldn't be dependent on the initial condition because it has nothing. Like the matrix is just the matrix. The initial condition
if you multiply it many, many times. Or, say again.
Right, I mean, obviously, because you're working with the same matrix, so the eigenvalues and eigenvectors are always going to be the same, right?
Yeah,
The,
okay,
the vector,
Mm-hmm.
yeah.
Okay. Okay, so now I created this matrix P where if the ant is at one end of the stick, it will stay there. Okay? This is called absorbing edges. And now let's just change the initial condition because we don't want it to start one end of the stick. Okay, so you see that I started here, and with time I got this bimodal distribution that is biased to where I started from. I mean, I can show you what happens if I start at 4. If you can imagine that it's the opposite. Okay? So here, I have basically, if I do this again, calculate what happens, I mean, the eigenvalues and eigenvectors, you see that I have two eigenvalues of 1, and they correspond to two eigenvectors. I have here two possible steady states because the edges are absorbing, and here I had, what happened in the end was biased by the initial condition. I got a linear combination of these two eigenvectors. Okay?
The weight will come from the initial condition, like
Yeah.
from here.
Mm-hmm.
Can you show us what's happened when you start with 3? Taking the middle?
Oh yeah, let's see that. I guess it'll be equal. Should be. There's nothing random here, of course. This is just multiplying the matrix again and again. So now the weights are equal. Okay. So okay, let's see. Let's do this again. And I actually don't remember what this says. Okay, here I had a detailed simulation where basically I used the transition matrix and I rolled randomly. Okay, so I had different initial conditions, and each time
The trajectory for each.
yeah, exactly. This is the trajectory for different initial conditions. And you can see that some of them go down there quickly and some not. Some take more time. And what I'm trying to show here is that Elad asked me to show what happens for 3. So the distribution for 3 would be equal for the two edges. But when you run the detailed simulation, you can have different initial conditions, specific trajectories behaving differently. Okay, that was just an analytical calculation of the distribution that you expect. Okay, now I have another interesting example that is the forward bias. So you can see I decided that the ant likes to move forward on the stick. It doesn't like to move backward, and if it's on the edge, then it has the probability to stay at the edge. Okay, and here we see that gradually, as expected, it should come here. I wonder what would happen if I run this one more time. Yeah, okay, so I keep getting this distribution because it does not dwell on the edge. It does not, the edge is not absorbed in. It can also go back, but the bias that I gave to going forward made the final, the steady state distribution made it skewed toward the forward edge, and then I can ask what are the eigen vectors, and you can see here I have only one eigenvector that is composed only of positive values. Let's do phi. Let's take this eigenvector, so it's all the rows in the fifth column.
Guessing it's gonna see that one.
Yeah. Okay, so this would be the distribution. And like we saw before, the eigenvalue for this vector is 1, okay? Like we require, and this will be the steady state distribution. So I showed you a steady state distribution that is not uniform, and I showed you a steady state distribution that is biased by the initial conditions, and it's a linear combinations of two of the steady states, basically. And here, and this is non-uniform steady state distribution. So let's take a break, and next period is given by Nadav, and I think what Nadav is going to talk about is very exciting because it applies these concepts of Markov chains and also dynamical systems that we work with a lot, and for a very interesting system that he's working on. Okay, you'll see.
To jest gorsze, ja nie wiem, czy nie wszystkim da się chyba napisać. Na przykład mają pierwszy plan. Jeszcze plan Jeśli proszę tak, ale
מגיע לבד?
זה עבודה.
לא, מה, זה בגלל רשתות?
לא.
יש רשתות?
לא, רשתות גורם לי להרגיש נחותה,
אה.
אבל כאילו, בוהה לעבר העתיד, לא? לא מבין את זה?
לא.
שנייה, מה עם זה?
אני שמעתי לעולם.
זה כזה...
מה זה הילד הנורמטיבי הזה?
לא, זה לא ידע,
שיטות,
זה
היא
חוויה.
בלבלה לי את המוח, אני חושב. שיגעת, אני כל הזמן מנסה לדבר.
נו, זה הקורס השיטות מחקר.
כן, זה משתלט לך על כל השבוע ועל כל החיים.
שנייה, למה את חושבת על השטחים?
לא על החיים.
אין לי גם משהו אחר.
בסדר, חשבתי שהיא לומדת איזה משהו כזה.
לא.
לא, היא גם נותנת לך טיפים לחיים.
טיפים. הוראות.
או שהיא...
לא? עשה ואל תעשה. בדיוק. מצוות.
הקורס הזה מבלבל אותי. אני חושב שהיה
לגמרי
דבר
מצוות,
אחד.
עדיף. מצוות. כולל מה עלול לקרות אם לא תסייפי. כולל לא תיובד. מה יקרה אם הוא לעבור על הדיווח?
זה השיעור האחרון שלנו?
השיעור אצלנו זה לא חובה להגיע היום, פשוט ביקשו שאני אשלים את החומר שלא הספקתי.
אבל זה טוב לא זה.
זה קורס שהסתיים בסמסטר א'.
רק שיעורי השלמה?
לא, הקורס נבנה ככה שהוא מתחיל כשדנה ויואב מסיימים עם הרקע החוץ. ככה.
אוקיי, באמצע.
כן. ואז הוא נמשך לעבר כבר שיעור.
זה כאילו...
אז הוא נגמר, אני חושב.
כאילו כולם למדו הסתברות
אני לא יודעת איפה זה. לא
בשנה הבאה אני אעביר קורס שרק כן, הם משנים את הקורס קצת. זה קורס של מודלים של נוירונים בודדים. דרכו לומדים דינמיקה.
In physiology, so are there presentations or is it?
No, it's Mickey.
It's the second
semester. Yeah, I think it's supposed to be that after each chapter in physiology, there's like the seminar. But
Right.
it just didn't, I don't know why. Luckily for me, it wasn't at the beginning.
I think it's nice actually, that structure.
Yeah, I think so too. It's really, I think it's a good course. Fine, doesn't it? My computer is not enjoying this. What's going on? Where is everything I need?
What are you,
What am I looking for? The stuff I saved yesterday when we were working and I, for some reason, decided not to do it in a very nice way. I just save stuff on the desktop, which is never a good idea. And come on, it has to be here. What is here? Yes, okay. Good. This is good.
last night I put together the reports for everyone in our group. But since no one knows how to write in English, I had to basically completely rewrite everything.
No, I think it's not fair. Probably know how to write, but not like an American.
It's debatable.
Why?
People, I mean, it could be that people here, like, are good at writing in Hebrew.
Yeah.
But
That's
it's
also
not.
Yeah.
not common. I mean, not because writing isn't so bad. Few people do it. Even when they are
Native speakers of the language?
native speakers.
Well, I feel,
Or even when they're like university educated.
Yeah.
well, I think that in
for PhD students, for example, if they don't know how to write in English, then it's a lot of work. They get a lot of comments from their advisors. They learn,
Yeah, I guess you have to.
that's what I think.
Some PhD programs have like courses in grant writing, actually, and it's
There's also a course in scientific writing.
right, and that's
Is it any
that
good?
too.
I don't know.
Didn't you take it?
I took it twice a semester.
Mm. Was it
There,
good?
there.
Their
It
courses
was
aren't
nice,
really
but
known as like the greatest.
their math of courses I thought.
Sorry?
Their math of courses I thought.
Okay.
But it was, I don't know, it was a good course, but it wasn't so useful.
Mm. Yeah, I think it's mostly practice.
Yeah. When I was in my bachelor's, I started working with a lab, and the head of the lab told me that I should start writing all my lab reports in English.
Mhm.
And,
In order to practice.
Yeah, to practice kind of more acceptable. So, it's a scientific work, so it should be written in English.
And so, what did you do in your bachelor's?
Chemistry.
Chemistry. How did you end up in just shutting down the computer?
I went to I went to study chemistry in order to go to university.
Really? You knew that?
Yeah.
Really?
I almost went, instead of going to the army, I almost went to study computer science the second round because I wanted to be a neuroscientist.
Okay.
And I did a regular army service, and I,
Decided on chemistry.
yeah, and I understood that probably will be better in chemistry.
Are there a lot of people that go to neuroscience from chemistry?
No.
I've never.
No, it's not the best
Not that
choice.
I know that many people in neuroscience, but still.
It's not the best choice, and it's actually relatively unrelated to chemistry,
Huh.
at least the way it's done here. Maybe if I would do pharmacology, it would
Mm.
come in handy. Or
Biochemistry.
yeah, or if I had
Yeah.
done something more molecular or protein design or something like that.
Mm. So
But
is it?
the main advantage was that I was good at it. I mean, I think if I would have studied physics, my grades would have been lower.
Lower, and then it would have been harder to.
Yeah.
Yeah.
So where did you pick up the dynamic and stochastic stuff? Such that you could be able
Here.
to teach it
Here.
in Alton.
Yeah. I took the dynamics course, and I worked on a model of a dynamic system, a neural network model, and I really worked a lot on it. So I would sit at home at night and find its fixed points and calculate the stabilities and the null lines and really investigate it pretty thoroughly.
Wow. Kind of
What?
it's optimistic, like that you can come without a background and work hard and
Well,
I guess
yeah.
you had a tendency for it or else you wouldn't go and do it.
I guess I have a tendency for math. And
Yeah.
I studied chemistry, but I didn't math as a physicist. I
Mhm.
studied chemistry to get more skills with math.
Yeah.
But I would say that if you really like something, it drives you to
To.
put a lot of work into it. For example, I learned things that I didn't learn in the dynamics course.
Yeah.
And it has a strong drive to, for me, it's like, I really want to see if I can calculate analytically the stabilities of the
Mm.
system, so I
Mm.
really pursue it.
Mm.
Sound segment sometimes included. Okay, so hello everyone. My name is Nadav. I'm a student at the lab of Professor Naftali Kishbi and Professor Eli Melkem, and I'm very excited show a application of the idea that you are learning in kind of real world research problem in neuroscience. What I'm presenting is my current research project, which titled Action Perception Model for Navigational Learning. It might go beyond some of the concepts you've been talking about in this course, but I will try to relate it to the two basic fundamentals of dynamical systems, dynamics, and stochastic processes, or more specifically Markov processes. But the underlying, so feel free to stop me if anything is unclear. The idea is to be a explanatory lecture and not just to present this work. And I want to start with the underlying intuition of what this work is about. So people like Naftali Fishley have this concept of the value information trade-off. And I thought of trying to explain it using this example. So imagine you want to go home, get to some friend's home or whatever, and you have two possible ways of getting there. So one is the bottom one. It's very straightforward. You just go straight all the time, and you will eventually reach there. But it might be very long. The other option could be much more complex, but you would get there quicker, presuming you know exactly where to turn and when. So the top example here, it's more complex. It's a more complex route, but it's shorter if you know where to turn exactly. The bottom one is less complex, but it's longer. It has less value in this sense if we equate the value with the time it takes you to reach them.
It could be shorter and not complex.
Yeah, there could be, but
It doesn't have to be something.
But often there's a kind of trade-off in the world between complexity and value. Actually, what this example maybe doesn't show very well is that very often we have many options with a sort of continuous range of value and complexity pairs. So there are usually not just two ways of doing something, there are many ways. But often there is a kind of trade-off between the complexity of the solution and the value. This is like a very sort of abstract conceptualization of this, but I try to make it more concrete with the research problem I'm dealing with. And this is building a model, a dynamical system model of the Morris water maze. So who here heard about Morris water maze? Okay, so not everyone, so I will say a few words. So it's a very widely used experimental paradigm in behavioral neuroscience, for testing spatial memory, navigational learning, and the way it works is that there's a large circular water pool, and mice are inserted in one of these four insertion points, and they start swimming, and somewhere in the pool there's a submerged platform. They can't see it. The water is usually opaque, and they start swimming. And if they reach the platform, they can get out. They don't like being in the water, so they have a motivation for finding the platform. Initially, they don't know that there's a platform, so they might stumble upon it. But if they don't find it, say after a minute or so, then the experimenter takes them out, puts them on the platform, and then they can look around, locate themselves. They have these visual cues on the wall, not necessarily this shape, but they have some kind of high contrast cues on the wall, and they repeat these trials many times over several days, and the mice eventually learn to reach the platform much quicker. So typically, an initial trial would look like this. They start here, inserted here in this square just go around, tend to like, being next to the perimeter of the pool. They just go in kind of circles, and sometimes they find it by chance. I mean, if they would go enough time, they would find the platform by chance. Here, for example, they didn't find it after 1 minute, and the experimenter took it out and put it on the platform. But after 4 days of such training, we see a very different kind of dynamics, where the movement is pretty much straightforward to the platform. And what I want to point out here is that in both these cases there is a kind of underlying structure to the movement. So in the first day, it's a kind of circular motion. So you can think of a kind of I guess you saw a kind of oscillator in this course. So you think of it as a kind of a oscillator, but of course it's not a perfect oscillator. There's noise here, as there is of course always in real world systems. And here it's a kind of a direct line, also noisy, but you can think of both these trials as something that you could perhaps model as a dynamical system, but with some kind of stochastic element. So I want to relate this to this concept of a Markov process, and I guess you've seen this definition. Okay, so the idea of Markov process is, I mean, stop me if you already know this, but the idea is that you have these states, and the current state, the present state, gives you all the information you need to know in order to predict the distribution of the next state. So, in some sense, the present state separates between all the possible paths which led to this current state and the next future state. And mathematically, we write it like this: the distribution of the next state given the current state is equal to the distribution of the next state given all the past. So all we need to know from the past is actually the current state. The more distant past does not give us any more information. And an example, you saw an example here, but here's just another one. So this is what I saw, I think, when I did this course. So imagine that the weather can be sunny, cloudy, or rainy, and that the weather today depends only on the weather yesterday. So we can present this process in this kind of state transition diagram. Have you seen something like this? I mean,
No, we didn't.
you didn't? Okay, so the idea is that each one of these circles is one of the states that the system can be here. Here is the state of the weather, so sunny, cloudy, or rainy. And these arrows just signify the probability of switching between these states. So if it was sunny today, for example, there is a probability of 0.6 that it will also be sunny tomorrow, but there's a probability of 0.3 that it will be cloudy tomorrow, the probability of 0.1 that it will be rainy tomorrow, and so on. This is also a kind of typical way of presenting a Markov processes or Markov chains, and more formally, we have I don't know if you used exactly this formalism, but probably something equivalent. You have a kind of probability vector which tells you what's the probability of being in any one of the states at a given time. So this is pi of t, the probability of being of the weather being sunny on day t, being cloudy and being rainy. You also have to define some initial distribution, and you have to define the transition matrix, how you switch between these states. So here the transition matrix, for example, looks like this, and the transition rule is simply you multiply the current state by the transition matrix. Sometimes it's written the other way around, like t times t, depends how you define the matrix. This is just a technical point.
The way that you presented that, it was a transpose of this matrix.
Yeah.
So here all the rows add up to 1.
Right. If all the rows add up to 1, you will write it like this. If all the columns add up to 1, you would write it as t times pi instead of pi times t.
And pi is the column.
Yeah.
With
want to point out, and maybe you've noticed this already, is that there's a very clear or very interesting analogy between Markov processes and dynamical systems, or in particular linear dynamical systems. In both of them, we have a transition rule, which is just defining the next state by the current state times a matrix, or matrix times the current state, and we have an initial condition. In this case, this is an initial distribution. And in the dynamical system, again, we have the state of the system at time t plus 1. This is a discrete time system, but we can do an analogous analysis for a continuous time system. And the state at time t plus 1 is this dynamics matrix times the state at time t. You also have to define the initial condition. So, at least mathematically, there's a very, very close similarity between Markov chains and linear dynamics. But the difference, of course, is that Markov processes define a stochastic process. I mean, time here defines probabilities of being in different states, and x here is a deterministic state. So this is a very sort of fundamental difference, but again, it's interesting to note this formal similarity. And in fact, perhaps one of the most useful models comes out from a combination of these two ideas, which is gives rise to what's called linear systems, or linear stochastic dynamics. And these are similar to the dynamics you saw, where x t plus 1 equals a plus xt, but there's also an added random element, some kind of noise, and the noise seems to be independent between the different time steps. And assuming that this noise is really independent, so at every time step there's some randomly drawn noise which is added to the system, we get a distribution of the state of the system which satisfies this Markov property which I showed you previously, that the distribution, now I'm talking about the distribution of the state, because the state is now a stochastic entity, and the distribution of the state at time t plus 1 given the state at time t is equal to the distribution of at the state at time t plus 1 given all the past. So all I need to know for the distribution of the next state is the current state.
Just to clarify, so the noise itself is not the Markov aspect of it, but the reason why it's Markov is because there's a deterministic aspect,
Mm-hmm.
which is dependent on the previous state, and then when you add noise together to that, so then you have the stochastic process where the deterministic part is relies on the previous.
Yes, but that's correct. But you also need to have this assumption that the noise is Markovian. That the noise is in some sense not dependent on the previous noises. So sometimes noise in nature has what we call the time correlation, where the noise at the current state can depend on what it was in previous states as well.
But it should be okay though if it only depends on the one previous state, right? If the noise is kind of just on one state back, it still satisfies Markov process, right? So everything is just dependent on the previous state.
Right. I think so. I have to think about it, but I think so. Yes. Was there another question? Okay. So a particularly interesting case of this kind of stochastic dynamical system is something that's called the Gauss Markov process, and this occurs when this added noise is Gaussian. So when the xi's are all normally distributed with some variance, there could be some non-zero mean, but it doesn't matter so much. And if this is the case, so something very interesting happens, because a linear dynamical system which is acted upon by Gaussian noise will always be Gaussian distributed. I don't know if you know this, but this is a very interesting and important fact about Gaussian noise, special fact about Gaussian noise. And this means that the state at time t will also always be a Gaussian with a time-dependent mean and a time-dependent variance. And we can compute, I'm not going to go into all the details, but we can compute the dynamics, the deterministic dynamics for the mean and for the variance. And we also need to provide the initial condition, which here is the initial mean and the initial variance. And then we have a deterministic dynamical system which describes the mean and the variance of the state at every time. And this is all we need to know because it's a Gaussian process. It's a Gaussian distribution. We just need to know the mean and the variance. And this is a very, very, very useful model because many systems, as you may have already seen, can be at least approximated by linear systems. And many kinds of noise, real-world noise, can be approximated by Gaussian noise because the law of the large numbers. I don't really want to go into this in the moment. But like I said, we have this dynamic for the moment, which are deterministic, and we have the initial condition, which is the distribution of the initial mean and the initial variance. And this is basically the model I'm using for modeling this water maze problem. And the way we're doing this is to start by defining the state of the mouse in the pool by looking at its position and its velocity. So perhaps you know from physics that if you know the position and the velocity of the physical system and you know the force working upon it, then you can compute the state at every future time. So I don't know how much physics you learned, but we're using a very kind of elementary physical model for the forces acting upon the mouse. So this is basically Newton's second law, where we have the x and y position, the x and y velocity, and the forces in the x direction has this restoring force minus k Fx, and this friction force minus gamma F dot x. So the restoring force, you can think of it as a kind of again, it's like a oscillator. If you've seen, the standard dynamics of the oscillator is. Okay, so actually I will wait. Maybe this is for the next slide. But the idea is that this restoring force models the circular motion we saw in this first day of the movement, and the friction models the dissipation of the water. So the mouse is to work against the friction of the water, and friction is usually proportional to the velocity. So we have a force which is in one is also proportional to the location. I mean, one element of it is proportional to the location, and this gives this circular element of the dynamics. In essence, this actually models the boundary conditions of the pool, because this is what causes the mouse to move in a circle.
So it's not something that attracts the mouse to the stage?
Right. It's not about the platform. It's actually about the center of the pool. I mean, so if you have what's called a harmonic force, which is directed towards the center of the pool, and the mouse has some kind of initial velocity, so this force will make it go in circles or in ellipses or in some kind of circular motion. Yes?
So then shouldn't it be dependent on the other coordinates? I mean, fx and fy?
Well, we separated, I mean, this is a vector equation, so we separated to, we have the x element of the force and we have the y element of the force. And we write a separate equation for the x direction and the y direction. This is a vector equation, right? So what I'm writing here is the x and y coordinates of this vector separated. But
the matrix would have mixed terms, maybe?
So, no, actually,
Wouldn't you say that if you're exactly at the edge, you can't go up, so it has a meaning on how you're going?
right, so
Like,
that's true. I mean, there is some kind of, it's a very non-linear effect of this boundary which is strict. The mouse cannot go through this boundary. But because this is non-linear, we are, instead of modeling this as a strict boundary condition, we are using this restoring force as a kind of approximation or a kind of proxy for this boundary condition. So the restoring force means that the mouse will tend to go in kind of circles around this platform, around this the center of this pool, and actually this is the way we are modeling the walls. Actually, the walls which are causing the mouse to do this circular motion. But because we want a simple model which we can analyze and a linear force like this is the simplest model we can think. You can even think of it as a first order approximation of any kind of nonlinear force which is causing the mouse to do this circular motion. So, yes, it's a bit confusing, I know, but the idea is that it's, it doesn't have to model exactly the physical process which is happening there. It just has to work, good enough. It just has to give a similar behavior to what you see. So this is a kind of intuition for this force. The friction, I think it may be easier to explain because the water does have a friction effect on the mouse, and this friction is dependent on the velocity, and this gives us this second element in the dynamics. And from Newton's law, so this is simply equal to the mass of the mouse times this acceleration. So the acceleration is the second. This dot notation, right? The dot indicates a time derivative. So this is m times the acceleration equals the force. And if we write this as a dynamical system, like I assume you did something maybe similar to this in this course, so we have here. I have to say something because I spoke about discrete system before, and now I'm talking about this is a continuous formulation. Usually in physics, it's more convenient to work with continuous time formulation, but eventually there's a way to switch pretty seamlessly between the two. If you're running a simulation in MATLAB, so MATLAB is always discrete, but I'm showing here the continuous time formalism. So the derivative of the state is the derivative of the position or the velocity, the derivative of the velocities or the acceleration, and this equals a times xt, and a is this matrix. So these two rows is just turning defining the velocity. So the velocity is simply the time derivative of the location, and these two rows describe the dynamics, what I showed you in the previous slide, in relating the state with the describing the fluctuations in the turbulence in the water, or maybe noise in the nervous system of the mouse. And the system eventually the dynamical system we get is x dot equals ax plus this noise. So this describes this kind of free motion of the mouse, what we saw in the first stage, this kind of circular noisy dynamics. But there is also, I mean, the interesting element here is what the mouse learns during this experiment. So the mouse also affects the dynamics by exerting forces. So how do we model the forces exerted by the mouse? So I just want to stop for a second because I feel like I'm losing some of you. Is there anything you want me to try and explain, or anything unclear?
Shouldn't the noise be time independent, and why is there a dependence in time?
So the noise is distributed Gaussianly at every time. So it's independent between times, but at every time it's like you draw a new variable at every time step. So this is what I mean by noise.
So far you did not talk about anything related with the motivation of the mouse, and how tired it is, or...
Right. This was only a kind of, we call it passive dynamics, or a free dynamics, how the mouse, it could have been also a different kind of, like an inanimate object. What are the forces acting upon it? So you have like the forces of the perimeter, which is this oscillating force. We have the forces of the water, which is the friction. But like Thor said, we didn't talk about the active components, what the mouse itself is doing. And
Only it will have a penalty for swimming fast because it has friction. It has something that will make it swim more slowly, or try not to swim large distances.
We also didn't talk about swimming at all. It can be a coin as much as it can.
yeah, so far it's just a physical object. We didn't talk about the forces or the decisions, the actions of the mouse. And this is actually what I want to introduce now to this model. And to do this, I need to, which time I have, but I need to at least mention a mathematical framework which is called optimal control. This is a kind of extension of dynamical systems. So if you like the course, I think you can take a course on optimal control that Naftali Tishby gives. I think it's also it's in the second semester, so it's probably ending next year if you take it. And optimal control takes you from this concept of dynamical systems, which like you've learned, just work in a kind of open loop, we call it. You have an initial state, you have maybe external forces, you have the physical laws, and this is how the system develops. But in a lot of real world applications, we also have some kind of agent, some kind of, in this case, the mouse, which can also affect the system. So the mouse can, exert forces to change his position, to move slower, to move faster. And the way we sort of abstractly describe this kind of problem is that we have some kind of reference signal. So in this case, in the mouse, it could be, the location of the platform where he wants to get. And according to this, he gives some input to the system. So in this case, it will be the forces that he's exerting. The system has some outputs, and the mouse measures, or the agent measures these outputs through some sensor, and adjusts his inputs accordingly to reach his desired target. I gave you another example of driving a car. So you have this controller, which is the driver, you have the system, which is the car, the physical car itself, and the driver has some map, or I don't know, some place he wants to, or she wants to get to, and she drives, and then she gets measurements, seeing the road, what's happening, where she needs to turn, if there's a red light or whatever, and changes her input to the system, to the car, with the gas pedals accordingly. So this is the abstract notion of optimal control.
The map in this diagram is the reference.
Yeah.
So the idea of a reference is that it's like some sort of representation of the end goal. Is that the idea?
Yeah.
So it's like motivation or I don't know, like an optimality function or something.
Yeah. In fact, in optimal control, we define, like you said, a optimality, or we call it a cost function. I just talked about it now. Formally, we have this linear stochastic dynamics, so the state depends on the previous state. There's this noise, sigma t. Note that here I'm already switched to the discrete time formulation, but there's also this u, we call this the control function, which is a new element which you haven't seen before, and here it represents the force exerted by the mouse. This is a active component which the controller uses to affect the state of the system. And the way this is determined, what this u is using, like you said, a optimality function, or what we call a cost function. And in our case, this cost function is a quadratic term which has two elements. One element is measures the displacement between the current location of the mouse and the location of the platform, or actually it's the current state of the mouse and the state of the platform, because the state, like I said, has location and velocity. The platform has velocity 0, of course, but never mind. This is how far the mouse is from the platform, in a sense. And the other one is how much force the mouse exerts.
In this model, you assume the mouse has already learned, the mouse knows where the platform is and adjusts himself in order to get there, or is it while he's learning, before he's when is this?
Right. So this optimal control model describes the situation when the mouse has learned. So after the mouse has learned, we are assuming that he's, in a sense, trying.
Working optimally, like he wants to get to the platform as fast as possible.
Yes.
That's that function.
Not just as fast as possible, but also using
At
as
least
least
amount of
amount of energy as possible. Actually, this would be an optimal mouse according to optimal control theory. But if you remember how I started this talk, said that, so this is what I called a value function. So like the length in the maze. But I said that there's also a complexity term. I will get to this soon. It's something that will be added to this cost function. But for the moment, we can say that an optimal solution to this problem would be a control signal which minimizes this cost function. And we have these matrices which weigh how important is this displacement term relative to this force or energy term. And I'm not going to go into it so much, but in the analysis itself, we use the data from the experiment to estimate these matrices, to infer or estimate what is the cost function which each specific mouse or the mice in general are optimizing. So we assume that this is actually a sort of rough approximation of what's going on in the head of the mouse. It's trying to minimize this kind of function under the constraints of these dynamics.
I want to understand why you add the control function only when the mouse knows the direction where it wants to go. Like when it doesn't know there is a platform, you also use the force which it wants to go.
Well, yeah, this is I mean, the idea is that when the mouse doesn't know where he wants to go, he will mostly work under the influence of these external dynamics, these forces of this boundary condition and the friction of the water, and this is why we actually see these mostly circular motions. It's kind of undirected, it's like a random walking, but still has this constraint of the physical world. But there is no control signal in the sense that there is no real goal, specific goal, or at least this goal. It's not something he even doesn't know where the platform is. So we don't really have a control signal, although it's true that of course the mouse has to use some forces to move around, but we are modeling these forces as part of this passive dynamics of the pool. Yeah?
If I understand you correctly, this describes the mouse at day 4, whereas the previous dynamic
Yeah.
describes it at day 1.
Yeah.
Can you model the way the reference influences the mouse to transition from that dynamic into this one?
Yeah. So that's exactly actually what we wanted to do, and before I get to that, I need to just say a few words about how to solve this problem mathematically. So this is actually a problem in optimal control, or if you learned classical mechanics or analytical mechanics, it's very similar, because we have a kind of generalized energy function, and we have a dynamics of the physics of the world. Oops. And we can solve it. I'm not going to go into the mathematical details, but we can solve this problem as a constraint optimization problem. It's called the linear quadratic regulator. Linear because the dynamics is linear, quadratic because the energy function is quadratic, and regulator because we are regulating this cost function. We need to find the forces which are minimizing this cost function subject to the dynamics. And the solution is a linear, again, a kind of linear displacement force. This is not the same K as before. This is a matrix K. And this means that the optimal force for reaching the platform, minimizing this combination of length and energy, would look like this. And we can use the matrices of the problem to compute this optimal force. Okay, so I don't want to go into this too much, but I will just show you what we get from this solution and how we compare it to the actual data. So what we see here is the empirical data on day 1. So as before, this is a kind of circular noisy motion, and the blue, this is a green line here, and the blue line here is what we get from the model of the free dynamics. So without control, just this matrix A and the noise. So it's more or less similar. Of course, it's not overlapping. There's noise here, but it's more similar than what we get from the optimal control model with after solving this LQR problem, which is the red line. So we have here 3 lines with the same starting conditions, and what I want to point out is that the blue here is more similar to the green than the red is to the green. Whereas if I look at an empirical path from the last day, so this now the green is from day 4, so now it looks more like the optimal control model, more like the red than the blue. Okay?
So what is free again is just the F equals ma dynamic?
Yeah, without U, without this control signal.
Why is it so more, like in the previous slide it was all over the place. Why is it more towards the center here?
I think this is just a random, because every time, you have a